Welcome to the first video in Chapter 2. This chapter is called Limits and Continuity, and we will be learning what limits are today, so limit notation, and then later on in the chapter how limits affect the continuity of a function. So 2.1 has a lot going on. This is not the title of 2.1, but this is the first video in this first section, and we're going to talk about limit notation, how we write limits, and then how to find them graphically. In this video, we'll be understanding what all of these values mean. You probably already know what f of a is. A is just any x value. This is just the output when you plug in a. It's the y value. But these are the three different types of limits that we'll see. These first two here, the limit as x approaches a from the left of f of x and the limit as x approaches a from the right of f of x are called one-sided limits. So this notation is good to just get written down. Those are called one-sided limits because they deal with either coming from the left or the right. And then this is the overall limit. It does not have a negative or plus here. It's called the overall limit. The limit as x approaches a of f of x. So I call this one the overall limit, or just it's the regular limit. And then lastly, f of a, we're going to discuss the difference between the limit as x approaches a of our function and then the actual value f of a. For our first example, let's let the value that we care about, that a value, let's let that value be specifically 1. So instead of x equaling a or approaching a, we're going to call it 1. So the way that we'd write those one-sided limits looks like this. The limit as x approaches 1 from the left of our function, f of x, and then the limit as x approaches 1 from the right of our function, f of x. Now limits are y values. So let's see what this really means. Our function is like nice and continuous, right? I don't have to like lift my pointer up at all. And if we're looking at specifically where x is 1, that's right here. Where is that on our function? That's right here, right? We would say that this is the coordinate point 1, negative 1, right here. So this is where we care about on our function. Approaching from the left, approaching x is 1 from the left looks like coming down here and approaching it from the left-hand side, just like this. Approaching it from the right is coming from this side. Let's think about what we're actually approaching. So as we approach x is 1 from the left, we're coming down here. What y value are we getting closer and closer to as we approach where x is 1? Well, we're approaching this y value down here, negative 1. We could draw that like this. We're approaching the y value of negative 1. And then how about from the right? Let's look at that from the right. So this is our right-handed limit, or right-sided limit. As we approach the value x is 1, from the right, coming down this way. And what y value are we approaching there as we approach when x is 1? We're approaching the same y value, negative 1. So it looks like our left-sided limit is negative 1, and so is our right-sided limit. It's negative 1. Because our left and right-sided limits are the same value, we can come to the conclusion, this means therefore or thus, we come to the conclusion that the overall limit as x approaches 1 of f of x is negative 1. We're not talking about what's happening exactly when x is 1. We're talking about the limit, what we're approaching as x is 1. And from the left, our y values approach negative 1, and from the right, our y values approach negative 1. Therefore, the overall limit as we approach 1 from both sides, the overall limit is negative 1. Now, let's talk about what is actually f of negative 1. What is that actual value? It's right here, that coordinate point. So this is a separate idea, and this is something that you already know. If I asked you to find what is f of 1, I want the exact y value when x is 1. That exact value is also negative 1. This is not always the case. There could be a hole in the graph there. There could be something else crazy going on. But this idea you already know. You learned this pre-calculus, right? Before the calculus class. This is saying, what is the y value when x is 1? It's -1. The limit is the y value that we're approaching. All right, let's look at another example. Here, our graph is called g, or g of x, and so that's why I'm using g of x here instead of f of x. It's just notation, it's what our specific function's called. Again, we're going to focus on the x value of 1. So let's take a look at what's happening on our function as x is approaching 1. So as we approach 1 from the left side on our graph, here's where x is 1. It's here and here, right? We sort of think about it in both spots, but if we're approaching from the left on our actual function, we're really getting close to this y value that looks about, I don't know, I'll say 4.2, okay? A little above 4. As we approach and get to where x is 1 on our function, we're approaching the y value of about 4.2. So I'm going to change this to like a little squiggly because I don't know exactly what it is. Graphically, we can never be exact. We're approximating. Let's take a look from the right. As we're approaching from the right, again, we're not hitting where x is 1. We're going where x is 2, x is 1.5, 1.2, 1.1, 1.01. We're getting really, really close to 1 from the right. The y value that we're also approaching is the same one. It's about 4.2. Oops. Do my little approximation here. And then I'll do the arrows. So we approached from the right side and we approached from the left side. And we're approaching that same value there. That value doesn't exist there. There's a hole. But again, limits are not about what it is exactly at that point. It's about what you approach. And we're approaching the y value of 4.2. Now, are our left and right-sided limits the same? Yes, they both exist and they're the same. They equal a number and they're the same. Therefore, we can come to the conclusion that the overall limit as x approaches 1 of g of x is approximately 4.2. We can come to this conclusion because if the left-sided limit and the right-sided limit both equal a number and they're the same, the overall limit is that number. Now, on a separate idea, you realize that our function value, when we plug in x is 1, it doesn't equal 4.2. It equals this value here, like 1.8-ish. So here's a separate idea. F of 1, the exact value when we plug in 1, is, again, approximately, let's say 1.8. It's different. But again, the limit is not about what we are at exactly that x value. It's what we're approaching. This graph, and we'll get to this idea later, this graph is not continuous at x equals 1. There's a hole there. So the limit exists and the function exists at that point, but they're not the same. But the limit is 4.2 because that's the y value that we're approaching as we get really, really close to when x is 1. Okay, here's another example of a graph called g of x. Let's take a look at when x is 3. And as we approach where x is 3 on our graph from the left side, we're approaching it here. So when x is like 2, when x is 2.5, when x is 2.9, 2.99999, right? What y value are we approaching as we go from the left? We are approaching, oh, that was bad. We are approaching a y value of 4. Do we ever hit it? No, but that doesn't matter. It's about what we're approaching. So our limit as we approach 3 from the left is 4. Again, limits are y values. All right, let's take a look at approaching x is 3 from the right-hand side. We sort of have to shift gears because now when x is 4, 3.5, 3.1, 3.001, where are we? We're down here now. That's to the right of 3. So we're looking down here. What y value are we getting closer and closer to as we approach 3 from the right? It's a different y value. It's -3. So our limit as we approach 3 from the right is actually -3. Let's check out that both of our one-sided limits exist. 4 and -3 are both just values, right? They're not infinity or they don't exist or something. They're just numbers. But let's take a look at our overall limit then. What's our overall limit as x approaches 3 of our function g of x? Well, do the left-sided and right-sided limits both exist? Yes. Are they the same? No. Therefore, our overall limit does not exist. It does not exist because the left and the right-sided limits are not the same. Let's take a look at the other idea. What is the value at g of 3? What is g of 3? Well, what is the y value when x is exactly 3? It's not up here. It actually is down here. The coordinate point 3, -3 exists. So the y value when x is 3 is exactly -3. Okay, here's putting it into really mathy terms. I just wrote this. I didn't look in your book or anything. Your book does talk about this if you'd like to look at it. It's not going to look the exact same, but this is exactly what we talked about. I like doing the examples with numbers first, so this is not more overwhelming than it needs to be. And honestly, if you're somebody that doesn't like writing this stuff in your notebook or your whatever, wherever you're taking notes, that's fine. But I do want to show you the mathematical side to it. So for any function, f of x, the limit as x approaches a of our function is this y value, L, right? If and only if, that's a cool little mathematical thing. If and only if the limit as we approach a from the left is L, and the limit as we approach a from the right is also L. Remember, the left and the right-sided limits had to both exist and be the same number for the overall limit to exist and be that number. If this is not the case, like in that last example, we say the limit as x approaches a does not exist, DNE. Let's take a look at one last example. We obviously want to focus where x is 6 here. So let's take a look at the limit as x approaches 6 from the left of our function, and we'll take a look at the limit as x approaches 6 from the right of our function. Now, this is sort of a point of contention in calculus that I've seen. Infinity, it's kind of a weird thing, right? If we take a look at approaching 6 from the left-hand side, our function is approaching positive infinity. I zoomed in on the, well, this graph is not showing everything, but it does continue infinitely north, right up there. So our y values are approaching infinity here. This is a horizontal asymptote. So what I'm going to do is actually write positive infinity there, because our graph does continue to go up and up. Our y values approach positive infinity. If we take a look at approaching 6 from the right, our graph is going down and doing the same thing but just in the negative way. So our graph is approaching negative infinity. Now, it is okay to write infinity or negative infinity. You can put a plus in front here if you want. It's okay to write those for one-sided limits. However, when we do our final limit, the limit as x approaches 6 overall, the two things that had to exist are that they had to equal a number, and that number had to be the same. Infinity is not technically a number. Now, even though they are different, that doesn't even matter. If they were both just infinity, this would not overall exist because this is not a number. So both reasons the limit doesn't exist is that A, they're not the same, the one-sided limits, but the main reason is that they don't even exist. They're not actual numbers. So we would say that this overall limit does not exist. The last thing that I want to say is that there are a lot of places to get great information online. You do not need to only look at my video if maybe you're still confused about something. I'd recommend either rewatching the part that you were confused on or maybe even looking elsewhere. I do get a lot of my pictures from the Khan Academy practice. That's a great resource online as well. So if you need to look at other resources, that's also totally fine. I am putting specifically what I feel like we need to know and using examples that I think are the easiest to understand. All right, best of luck. I hope that you are understanding how to find limits graphically after watching this video.